I hope you are doing okay. Last time, if you remember, okay, we did the refrigeration cycles. Okay, I've done 4 problems, I guess, and there is a 5th one I uploaded. Okay, so 1 minute, please. Yeah, sorry for that. I had a network problem. Okay, we've done, if I remember, okay, let me check. Yeah, just shared and recorded. We've done 5 problems. Okay, I've done 4 and 1 I uploaded, and there's this one, the cascaded one I uploaded in details. So for today, we will be doing the psychometric chart. Okay, let me put here a group session. Okay, and let me upload the psychometric chart. So, okay, 1 minute. Yeah, so for chapter 14, there are 2 methods to solve the problems: the psychometric chart, and there is the equations method. I will not go through the equations method because like it is very long, and usually the professor doesn't even include it, okay, because it is very long. And even if he included it, like what you'll have is going to be maximum of 2, 3, 4 things to do, because for each property, okay, for each property, you need to use an equation. And then for the second property, you need to use an equation. It's not like the psychometric chart where, like now, if you just got 2 properties, now you have all the properties done for you. Okay, that's the advantage of using the psychometric chart. Like you only need 2 properties in the psychometric chart, just like the thermodynamic tables. Okay, first let me explain or start by showing you what are the different things that we have in the psychometric chart. So let's say that we have an airflow, okay, at let's say 30 degrees, okay, 30 degrees dry bulb temperature, okay, dry bulb temperature, and maybe 50% relative humidity, okay. So you go, this is the axis of the dry bulb temperature. You go, yeah, this is 30 degrees, and 50% relative humidity is gonna be this line, okay. So here, the intersection between this line and this line. Okay, so now you located the point. Now you can give me any property, or I can give you any property only from these 2 things. Yeah. Now what is approximately the specific humidity? We go to this axis, and now this is the specific humidity, okay, or the humidity ratio. So it is, let's read the scale. This is 12, this is 12.5, this is 13, so it is 13.5. Okay, 13.5. Pay attention to the units. It is in grams of moisture per kilograms of dry air. So grams of H2O per kilograms of air dry, okay, or dry air. Okay, if you want to convert it to kilograms per kilograms, you have to divide it by 1000. And then let's say that we want to have the wet bulb temperature. Okay, you see like there's very, very fine lines. Okay, I don't know if you can see them with me, but the lines that are dotted, okay, you see the lines that are dotted are the wet bulb temperature lines, because here you can see 25 degrees wet bulb temperature, and here with this dotted line, they're not exactly parallel with the enthalpy lines. Okay, there's like again network. I guess the network problem stopped. Yeah, they are not exactly parallel with the what do we call it? Yeah, the enthalpy lines. They are slightly deviated. Okay, so follow these fine lines, dotted lines. Okay, and go to your wet bulb temperature. Now I have my point here, so I'm not in either of the 2 nearer lines from me, so I can do a parallel one to them. Okay, those 2 dotted lines, and you can go like this, like this, like this with your ruler. Draw a parallel line to those 2. Yeah, and I hit my wet bulb temperature. Okay, so this temperature is the wet bulb temperature. How can you read it? You can either read it from the scale, but I don't prefer that. You can go directly down. Okay, so here you can go straightly down there, and you'll find here. Okay, what's the temperature here? It's 22. Okay, or you can read it from this scale. Doesn't matter, but like it is easier to go down and read exactly what is the temperature there. Now we got the dry bulb, we have the humidity ratio. What is else left? Yeah, there is also another property you can get, which is the dew point temperature. Okay, dew point temperature, which is this here, this temperature here. You go straight line, and now you go down. It is approximately, we have here 20, we have here 19, and we have here 18. So it is approximately 18.5, okay, 18.5 degrees Celsius. This is the temperature where the dew will start to form without adding any moisture. So if we say that our moisture is, let's say this is the moisture content in air, and let me say that this is an air particle. Okay, so this is air particle, and this is the moisture content, moisture inside this air. So without any changing, okay, in the moisture content, when will the dew starts to form? So when will this air bubble close exactly to contain this moisture? Okay, so I'm only doing? I'm only taking temperature, okay, from the air. So I'm only extracting temperature from the heat or taking heat from the air till the air. Now, when you decrease the temperature of the air, the capacity of the air to hold more water or moisture will be less. So now the air bubble will be something like this. Okay, now the air will be like this, and like this, and like this, till the air coincides with the moisture content. Now, any decrease in temperature further will make me lose moisture. So this will happen, okay? You will slide across this line. This line is in fact the 100% saturation, okay? So now the air is completely saturated. Any further decrease of temperature here, your line will go sliding like that, okay? That's what will happen. And you cannot leave this line unless you add temperature, okay? Of course, this is the ideal case, and we don't discuss anything in this course than the ideal case, okay? Later on, I will show you what I do mean exactly by the ideal case when I solve an example. And what else we also have? But the wet bulb temperature is the temperature where I'm going to have, look here. Okay, so we have a bulb, say this is the bulb, and this bulb is dry. Now the air will go through this bulb. This is the dry bulb temperature. Okay, they like, let's say the normal temperature of air. Without anything or without any tweaks or modifications. So, but this temperature, the wet bulb temperature, is the temperature that I measure when I have a wet here, okay, a wet cloth, okay, that is surrounding the bulb, okay, and I have now my air is going there, okay. Now, if my air is not 100% saturated, then it will take some of the moisture in this wet cloth, okay. And taking some moisture of this wet cloth, what is the temperature, okay, of the air after it passes here? So it is a kind of a measure of the humidity for air, because we cannot measure humidity by like conventional devices. Now, yeah, we can measure it. We have many things to do, but in the past, like let's say, yeah, you want to measure the temperature of the air, you have the thermometer. But how can you measure the humidity of the air? Okay, there is no thing to measure the humidity. So what happens is that if your air is not 100% humid, then it will take some of the moisture here, and you'll have a temperature reading there. Okay, so this temperature reading will identify or will tell you how much humid is your air. So this is our air. It is approximately 50%, okay, humid relatively. And then when you measure this temperature, okay, so this is the temperature after it goes through this wet cloth. It is approximately 22. You see how? Okay. Here's the temperature after it passes the wet cloud. If your air, when your air become more and more and more humid, so let's say that our air is in this point, okay, and this point is in fact I have it at 28, yeah, 28 dry bulb. So what is the wet bulb there? So like that, the wet bulb is approximately 24.5. Okay, so the more and more your air is humid, the more and more the wet bulb temperature will be close to the dry bulb temperature. Okay, till your air is 100% saturated, then your wet bulb temperature is equal to your dry bulb temperature. Because when the air will passes this cloud, you will not have any gain of humidity. Okay, so nothing changes. This air is already 100% humid. What else can it take? Okay, so yeah, that's it. And let's start basically solving question. Oh yeah, there is one thing I forgot, sorry. The enthalpy. Okay, the enthalpy lines are the solid lines that you can see here. Okay, and also the volume lines, okay, are the lines that are going in that direction. Okay, so here you can see some lines. Okay, this. These are the volume lines, and the enthalpy lines are this. Okay, how to measure the enthalpy? Just go straight, like with the lines, take a line parallel to them, and go straight there. Okay, and you will hit here. Okay, the outer scale is for the enthalpy, and the volume you just make like interpolation between those two lines. Pay attention that you need to be very accurate in using the psychrometric chart. Okay, the exam will be in person. Okay, you need to be very accurate. Get your ruler and just get the value exactly there for the professor. But if it is on computer, then you just like select the point. Okay, like that, and just like I'm doing, and because yeah, you don't have that much of accuracy using the mouse. Okay, what is the first problem? Okay, let me look at the first one that I prepared for today. Yeah, 1 minute. Yes. So I'll try to solve like problems that have like something new to them, something special to them. Okay, so that you get the benefit of the tutorial. Okay, so it is problem 1487. Okay, 1487. Yeah, like this, like this. Okay, and here like this. Okay, so we have air, okay, that enters a cooling coil. Okay, so now this is my cooling coils. Okay, and air will enter the cooling coils at temperature equal to 39 degrees Celsius. Okay, when he gives you just temperature, then you know that this temperature is definitely dry bulb temperature. Okay, and then my humidity Y, okay, is 50%. So this is cooling coils. Cooling. And then after the cooling does happen, you have a heating coils. Okay, so here heating. Okay, and then after the heating is done, okay, my temperature will be 17 degrees Celsius, and my T wet bulb will be equal to 10.8 degrees Celsius. So what I need to figure out, I need to sketch at first the problem in the psychrometric chart. So A, sketch. Okay, of course, the pressure is 101 kilopascals, which is the pressure or the atmospheric pressure. This pressure allows me to use the psychrometric chart. Otherwise, I have to use the equations. Okay, and B, because the psychrometric chart is only done for air at atmospheric pressure. You might find other psychrometric charts that are done for different pressures, but the one that we use is the one that's there for the atmospheric pressure. And when the pressure is different, we need to use the equations. B, we need to determine the dew point. So the dew point, dp. Okay, the dew point temperature of the mixture at the inlet of the cooling coils and at the inlet of the heating coils. So dp here, TDP here, and TDP here. Okay, in the inlet of the inlet cooling, and also for heating. And then C is that we need to determine the dew point temperature. What is the net heat transfer of the entire process for this? Okay, so what is the net heat transfer? Net heat transfer. The heat that is transferred from the cooling coils, and then the heat that's transferred from the cooling coils, net heat. Yeah, and yeah, the problem is with 1 atm. Okay, so let me just double check that I took the values correct. 39, 50%, 17, 10.8. Yes, everything is cool. The cooling coils first and the heating coils. I need to sketch the dew point. Okay, everything is done there. Yeah, so this problem, as I told you, 1487. Okay, and this is, I think, the only problem where you have cooling then heating together, because those two processes are simple. Those are the simplest processes that you can have in a psychrometric chart. But what if you have them done together? Okay, so cooling then heating, or heating then cooling. What is happening there? Okay, first to sketch the problem in the psychrometric chart. Okay, let me delete here what I put first. Okay, so this explanation. Yeah, okay. Delete. So at first he tells me that my temperature is 39. So 39 just before 40 and go up to 50%. This is the 50%. And let me make the line thicker. Maybe this will do fine. Okay, so it's approximately here. Oh no, this is the 40. So let me go above a little bit, and yeah, this is the 50. So now I have air at 39. Okay, where am I? Oh no, I put it. You have to be very careful. Okay, this is the 40 and this is the 39. Now it is with the 50. Yeah, that's correct. So this is 0.1. Let's just mark it there and say 1. Okay, in a different color. Okay, yeah. Let me say this is 0.1. Okay, and then 0.2. Where is 0.2 located? 0.2 is 17 Celsius. Okay, and 10.8 wet bulb. So where's 17? 17 is somewhere around here. Yeah, this 17. And how to know the wet bulb? The wet bulb is coming from these lines. Okay, as I told you. So you can see, like, this is the 10. This is the 10.08 somehow. Okay, 10.08. So I'm gonna go with very fine lines. Okay, let me put them, mark them with very thin to make it somehow accurate. I'm going up, and then I hit here. Okay, so here I hit here. Then I go in lines that are somehow parallel to these dotted lines. Okay, the dotted lines are for the wet bulb temperature. Okay, so where are the dotted lines for the wet bulb temperature? Okay, let me go. These are the dotted. So I'm gonna go parallel somehow. Yeah, guess I'm managing to do them. Okay, but you got the idea. I have to go parallel to these small fine dotted lines. Okay, and my 17 wet bulb. So 1, 2, 3. So yeah, is around here. Around here, I'm gonna have my interaction. Okay, so this is 0.2. And what happens at first? I'm having cooling. Okay, simple cooling. So in simple cooling, what does happen? You go in a straight line to the left. Okay, straight line to the left, because simple cooling, no addition of moisture, okay, or taking of moisture, anything. Okay, Now, after you hit this point, what happens? I've told you, if you hit the 100% saturation, then there is no going back from it unless you add temperature. So we'll keep sliding across this line. Okay. Yeah, keep sliding till you reach this point. Why this point? Because at this point the heating will start. And how did I know? Because this is a simple heating, and the simple heating need to be straight line. So I went where I can find the straight line with this one. Okay, so what you realize here, you realize that they continue, okay, the second process continues from the dew point temperature of it, of 0.2. Okay, I cannot do a straight line, but I guess you get it. Let me do it much better. Maybe with the green line, I can do it a bit better. So I keep sliding. No, it's not better, but yeah. Let's do let's work with what we have. Okay. So yeah, this is what's happening exactly. And this is the cooling process. And what is happening here? Here we are losing moisture. Okay, so here we have some condensation, and in fact you can calculate this amount of moisture that is condensed. Okay, and here we have the amount of heat added. Okay, so here we have heat addition, and here we have heat extraction, and here we have condensation. Okay. So yeah, so what is the first thing that is asked from us? To find the dew point temperature at the inlet of the cooling coil. What is the dew point temperature at the inlet of the cooling coil? It is here. Yeah, and the dew point temperature at the inlet of the cooling coil is around, let me see, yeah, it is around 30, 39, 38, 37, it is around 26.5. Okay, so the dew point first at the inlet of the cooling coil. Okay, let me call it 1. So this one is 26.5 Celsius. And here at the inlet of the heating coils, here I'm entering the heating coils. So this one is approximately 4 degrees. Okay, so T dew point 2 is approximately 4 degrees Celsius. Okay, these are direct information straight from the psychrometric chart. You see how easy it is? Yeah, and then I need to get what is the amount of heat that was added in the total process. So first, this amount of heat from here to here. Okay, I don't have, I think, the flow rate. Okay, since I don't have the flow rate, okay, or the volume rate, I cannot give him the exact amount of heat. Okay, so m dot multiplied by q. Okay, because if I have the V capital at the inlet, so the volume, the amount of volume that's entering, I can divide it by the specific volume here, and I can get the m dot. Okay, and after I get the m dot, I can know what is this here, the moisture that was condensed here, as I told you, condensation amount. And then from the condensation amount, I can subtract it from the mass and then continue here using the new mass after the condensation for the heating process. But I don't have the capital volume here or the volume flow rate here. Sorry, the volume flow rate, not capital volume, also capital V dot. Okay, so I have to get for him the specific heats. Yes, and how to get the specific heats? Well, it's easy. H minus H, H minus H. That's all you need to know. So here, this is the H here. Okay, at the beginning of the cooling process. Yeah. And what is the H at the end of the cooling process? Okay, this is here. Yeah. So from here to here, and then H minus H here for the heating process. Okay, just let me check the values. Okay, that we got here from the psychrometric chart. Are they close to the accurate ones or not? Because I didn't do the lines very fine. Okay, I'm doing it with the mouse. So what is the number of the problem? 1487, yeah? The problem with heating and cooling. Yeah. Okay, so it says that the first dew point is 26.7. Yeah, we managed to get that good. We got it as 26.5. And the second dew point is 5.3. Yeah, this one we messed it up a little bit. It should be 4. Okay, it should be 5.3. I put it here as 4. Maybe if I follow the line a bit better, maybe I can reach to there. Okay, or maybe I've done this one maybe not correct. Maybe. So let me put this as 11 here. Maybe, yeah. Maybe the point should be somewhere around here. Okay, and then when I go to there, yeah, I'll find that it is 5 point something. Yes. Okay, and what else we have? So now we need to find the amount of heat. Okay, or the heat, as I told you, the specific heat, not the total amount of heat, because I don't have the m dot. Okay, so what is it for the cooling? For the cooling, it's going to be H minus H. Okay, and then for the heating, it's going to be the same thing, H minus H for the heating. Okay, or we can do something. Okay, I see that the book here done it, is that he puts the amount of heat that was transferred with cooling. Okay, so for the total process, and then he subtracts the amount here. Okay, oh sorry, I did a mistake, small mistake there. Okay, so for cooling it's from here to here, okay, and for heating it's from here to here. Okay, this amount of heat, okay, so from here till here, that was lost. It's not due to cooling, it's due to the water being condensed. So I want to know what is the capacity of the cooling that I need to give, and what is the capacity of heating I need to give. So I can do like H minus H here, and then H minus H here. Okay. Or what he did is the first H minus this last H, and then he subtracts this amount. Okay. So this amount, as I told you, the amount of the condensation, it is m dot. Okay, this is the end of the condensation, omega here. What is the omega? Okay, minus omega. Okay, so I get the specific humidity here, I get the specific humidity here, and I subtract them. This is for the amount of moisture. But what is the heat that is accompanied with this moisture? So just the omega ratio multiplied by HW, okay, for the water. Okay, HW for the water. And you need to get that H at which temperature? 1 minute. Okay, you need to get that H of water at 5.3. Okay, so you need to get it at 5.3. So the outer H, okay, of the condensation process, or like the lower temperature in the condensation process. So it starts from 26, then it ends at 5.3. Okay, at 5.3. So you get the saturation temperature there. Okay, I guess the sharing disappeared. 1 minute. Share again. Yeah, my window. Yes. Okay, so yeah, here this one we found that this was 5. Okay, and you do what is H saturated. Okay, HF at 5.3 degrees Celsius, or 5 as I got it from the psychrometric chart. You find it, and then omega minus omega multiplied by HW. But let's just do the easier way. Okay, the easier way around. Why like bothering ourselves with this? Let's do here H minus H, H minus H. So what is H here at the inlet? Okay, I've messed up the point, so we might have some deviations. Okay, what is H? I can go with the solid lines, and in fact I can see that this is going like that. Somehow my enthalpy here is 97. You can say, or not 97, 98. So 90, yeah, 98. And I can say that my enthalpy here is around 88 as well. So here I have 10. Okay, so 10 kilojoules per kilograms. And in the heating, I have around let's say that this one is, so here we have 20, here we have 19, here we have 18, 17, 16, around that. And this line is approximately. I'm not going that carefully, okay? So please consider that. So this one is 32. Okay, so 32 minus 16 is gonna be 16 as well. And then with that 10, so we are gonna have around 26 kilojoules per kilograms. Okay, let me check that value. Hope that we get it a bit close. No, it's not close at all. So 26.5. Is he calculating something different? 26.5 kilojoules. So 96, yeah, and then 31 for that one. Yeah, and then subtracting the humidity. I don't know what is happening. Maybe he's calculating something else. Let me check. What is the net heat transfer? Oh, so what is the net heat transfer for the entire process? Okay, it's not the, so we have to do that, in fact. Okay, we have to do that. Yeah, this is because this is heat out from the condensation, okay, and this is heat out from the cooling, and this is here we have heat in from the heating. Okay, so what is the net heat transfer? It is gonna be the cooling, okay, and minus, let's say that the cooling and minus, and then minus the temperature lost from the humidification, from the condensed, and then plus the temperature coming from the heating. So that's what we need to do. Yeah, sorry, I thought we need to calculate the capacity of the cooling coil and the capacity of the heating coil. So how much heat was added here, how much heat was taken from here. Yeah, so okay, we figure out that this one is around 10 kilojoules per kilograms, okay, and minus, and the heating is around 16 in positive. And let's say you see what is the condensed heat, okay? So the saturation temperature at 5 degrees, you can get it, okay, from the tables. I will get it here online, okay? So saturation temperature at 5 degrees, at 5 Celsius. So, or not the saturation temperature, the saturated water, okay, the saturated water enthalpy. Oh, what is the saturated water enthalpy? Let me go to the book and go to the tables. Sorry, I don't have the tables with me now, so I'm gonna need the book for that. And it says that the saturation water enthalpy, at 5 degrees, it is around 137.75. Okay, that's the saturation water enthalpy, 137.75. Okay, don't go to the saturated steam, go to the saturated water. Okay, saturated water, okay, HF at 5.3 Celsius. Yeah, at 5, I go, yeah, it is around 21.02. Okay, so let us go back to our question. So HF at, okay, as I told you, at the outlet of the condensation process, 5.3, okay, or the lower temperature in the condensation, it is 21.05, 21.02, and then multiplied by the difference in the humidity. What is the difference in humidity? Just roughly there, very roughly around 5 here, because each division is a half. So here we have 5. What we have here upper, just very roughly, around 22.5. Okay, subtract them from each other. We are going to get 22.5 minus 5. This is going to be 18, okay. 19, 17, 17, 16, 16.5, yeah, 16 plus 5 is 11, it's 21, and then multiply, so 17. Okay, so 17.5. Okay, and this one you need to divide by 1000 to get the actual or the kilogram per kilogram. Okay, and now this one multiplied by this one. Okay, so it is 21.02, 21.02. Let's see how much is that. Okay. Why I can't find my calculator? Yes. Yeah, 22.5 minus 5 is 17.5 divided by 1000. Okay, multiplied by 21.02, and then plus the how much amount we had. From before we had here around minus 10, yeah, minus 10, and then here around plus or positive 16. Still there's something wrong. What is it? Yeah, the upper and the lower. Okay, from here to here, no need to put this one. Okay, so from here it is 98. Okay, let me know with this one. Okay, this one was when I was calculating the cooling. Okay, so let's see. The cooling capacity is from here to here. Okay, just to not make you confused. And then the heating capacity is from here to here. Okay, and the amount of cooling, okay, that was added from the humidification is from here to here. Okay, so what we need to consider is that the net heat transfer is from here to here minus the condensation. Okay, so here, so this is the only way to do what is the book asking for. Okay, so this one is 98, and this one is 32. Subtract them from each other. So I have 66, and then this answer multiplied by 7 or negative 17.5 over 1000 multiplied by 21.02. Okay, so I got 65.63. Okay, this is my total amount of heat transfer or the net heat transfer. Okay, of course it is cooling. Net heat transfer is in cooling. Okay, so from here till where? Till there. Okay, subtract from it the amount that was transferred. This because it's not heat transfer, this is mass transfer, but it will take some heat with it from the condensation. Okay, I hope you find it clear. Okay, this question is not that tricky, but it's a bit like to understand, like, yeah, I don't have only one process, I have two processes going from each other. So the net heat transfer is from here till there, and then I should subtract the amount of condensation that is happening. Let me show you the schematic diagram for the problem. Okay, let me change the share again, share here. Yeah, this is the okay, and the problems. Total. Okay, you can see air is entering from here, it's leaving from here, net heat transfer from here to here, minus the amount that was condensed. Even if you don't have this here, condensation pipe, okay, you have to understand that there might be some condensation. Okay, so definitely if I have the inlet from here and have the outlet from here, then the heating is going to be starting from the dew point at these properties. So what is the dew point at these properties? This is the dew point at these properties. Does it match that dew point? No. So definitely condensation happens. Okay. If this one was matching this one, so it was here, then I will have cooling and then reverse heating. They are working on the same line. But no, I have some amount of condensation there. Okay. Yeah, so that's it. That's basically it. This is like the hardest question that you can get in the simple processes. Something that I told you to know is that in heating, we can have heating, and then we have here a spray that will give me, the spray will give me humidification for the air. Okay, so that's how I simulate heating and humidification in the psychrometric chart. I'll go like something like that. Okay, so I have the straight line where I have only heating, simple heating, and I have the straight line up where I have the humidification. Okay, so the net process will be something like that. But in cooling and dehumidification, okay, the same thing cannot be happening. Okay, in cooling, simple cooling, okay, I don't have a device that does dehumidifying. When I want to dehumidify, my cooling coil, okay, should be at a temperature lower than the surface temperature here, should be lower than the dew point temperature in order to condensation to happen. So what happens is that I go like that, I slide across this line, then I end up where I want, okay? And this will be my line process. I cannot control going like this, like this, like this. Okay, I have to definitely slide along this line. Of course, there is a way, but this is the ideal process happening. Okay, these processes are happening not simultaneously, like first heating, then humidification. But here they're happening at the same time. Okay, just when I reach the dew point, then I'm going to be cooling with humidification. Sorry, with condensation, or which is dehumidifying. Okay, I'm decreasing the humidity. To go on processes like this, like this, like this, what happens is that I will let my air not all pass the coils. Okay, so some of the air will escape from here, some of the air will escape from here, and then these streams of air will be mixing here, and then from that, okay, some lines are going in this way, but some lines are not going in this way. Some lines are going straight and just stopping. Okay, so they all have simple heat, simple cooling. So if you mix those lines, you will get some things like that, like that, like that. Okay, of course, you are always limited by the maximum thing. So of course, you cannot go something like this. Okay, maybe, but you can go something like this, like this, like this, within the regions of your line. Okay, yeah, that was it for the cooling. What I meant by 100% efficient. Okay, we will not discuss these things. These we will discuss it in HVAC course. Okay, we only take the case where we are having 100% efficient cooling coils. Okay, so you will always, if you have cooling, simple cooling, you will always slide across this line, and you will end up at 100% humidity relative. The only thing that will take you back is that if you make mixing from here, or if you make heating, like here we have simultaneous cooling and heating. Okay, but for heating, I can have heating and humidification. Okay, let's see a problem where we have heating and humidification. Just give me a minute. Okay, and then we will only have the mixing problem left. Okay, for us, we only have the mixing problem. Yeah, there's also the one I forgot. Keep forgetting in this chapter, I don't know. Yeah, there's one where we have the cooling towers. Okay, so the cooling towers are just like the same thing, but we are like having more and more and more lines or more processes here and there and there. Okay, and there's also evaporative cooling. This one is an easy process. Okay, maybe let's do something with evaporative cooling. Okay, maybe if I have some time, I can go through something with heating and humidification, and if we don't find anything, then yeah, we will do it with the mixing. Okay, so problem 1493. Okay, we have air that enters the evaporator. Okay, let me share from here. Okay, we have air that enters the evaporator. Okay, let me delete. So air will enter the evaporator cooler, okay, or at 180 M. So we can use the psychrometric chart. We have it entering at 40 degrees Celsius. and at 20% relative humidity. Okay, at a rate of 7. You see what I meant when he gives you this volume flow rate per minute, and it leaves it leaves with 90%. Okay, relative humidity. Determine the exit temperature of the air and the required rate of water supply to the evaporative cooler. Okay. So 2 things I need to determine. What is the exit temperature of air, and what is the required rate of water supply? So T2. Okay, exit temperature, of course, he means the dry bulb temperature. And what is the required amount, m dot, of water supply to make this evaporative cooling? Okay, so let me explain the process real quick. Okay, I have here my duct. Okay, and this is the flow of air going like this. Okay, what happens is that I do inject some amount of water spray. Okay, but this air should be it should be cold and dry. Okay, this air should be cold and dry. And when I have this cold and dry air, and then I give it some humidity, okay, there, what will happen is that it will cool. Why is that? Okay, let me show you here in the psychrometric chart. Okay, so I want very cold air but dry. Oh no, I want a hot air and dry. Okay, sorry, not cold and dry, hot and dry. Okay, you don't see this here, okay, in UAE, but you might find it somewhere else. Okay, so here we have hot but dry. Okay, so not very high on the scale, but very high on the scale. So somewhere around here. And now when I pass this hot and dry water, hot and dry air through water, what will happen? It is hot, so it has high capacity of taking humidity. Okay, and remember, this is the air cloud. It is hot, so it has very high capacity. But in fact, what it actually has is something like this, very small. So when this air passes water, it will take much of its humidity. Okay, and when it takes off the humidity, okay, on that water that it passes through, it will cool. Okay, so it will cool. But the process is done on a constant enthalpy line. Okay, so this is the process where we have constant enthalpy, just like in imagine if it's a throttling process, but in air cycles. Okay, so when you have a refrigeration cycle, you have the throttling valve. Okay, you have H is constant, H in equal to H out. Same thing here, H is equal to H, if you just want to solve it directly. Okay, so here we have a certain H. Okay, and this line, the process will go on this line. It will stop at 90% relative humidity. Okay, he told me that 90% relative humidity. Otherwise, if it stopped here, then there is no escaping. It will keep sliding there or there. Yeah, and here in the inlet, I have some 20, okay, 20% and 40. Okay, so let me do it here quickly. Okay, so I need to know what is the mass flow rate of the air injected, of the water injected to make this process happens. And I want to know what is the outlet temperature there. So 40 with 20, I'm gonna stop here. And then with a constant enthalpy, okay, go with constant enthalpy. Where is the enthalpy lines? I'm gonna draw a parallel one, something like that. Okay, so the enthalpy is around, let's say 65. Okay, and I'm going with this constant enthalpy till I reach this point, which is 90%. Why this? Because this process is evaporative cooling. So what is the temperature here? Clear, it is 23 Celsius. So I found the first thing. You see how the psychrometric chart very easy to use once you know everything in it. And then what is the amount of water? Okay, so the amount of water, as always, I've told you, this is omega 2, this is omega 1. So here we have omega, okay, omega 2, omega 1, and then it is going to be m dot, okay, the m dot of air, omega 2 minus omega 1. Yeah, because this is the change of humidity. Okay, this is the change of humidity. And this change of humidity is going to be supplied by the water that was sprayed. Then I'm going to be multiplying it by m dot by, because the change of humidity is in which units? It's in units of kilograms or grams of H2O per kilograms of dry air. And the mass flow rate is for the dry air. So kilograms of dry air per seconds. Okay. So cancel. I'll have kilograms of water per second. Yeah, that's it. If you also want to do it in unit conversions, then that's what you end up with. You want to know the water, kilogram of water injected per second. Okay, but the humidity ratio only, or if he tells you what is the humidity increase, then you say omega 2 minus omega 1 only. Multiplied by m dot, now you have the amount of water injected, okay, in the process. Okay, multiply if it was cooling, okay, cooling like that and going like that, okay. So you say omega minus omega, multiply by m dot, this will be the amount of water condensed, because here I have condensation. If you have heating, okay, heating and humidification, yeah, this one will be the amount of water, okay. So this omega and this omega, so this will be the amount of water injected as well. Okay, so in heating and humidification and in evaporative cooling, I have water that is being injected through a spray. So what is the omega here? I can say it is around 16.5. I can see here it is around 9.5. So 16.5 minus 9.5 multiplied by m dot. I'm given in the question not m dot, I'm given v dot. Okay, so because I'm given v dot, I need first to calculate what is v. And very luckily we are v at the inlet is 0.9. Why I should do it at the inlet? Okay, because he told me this is the amount, okay, of flow rate in the inlet. So I'm using V small in the inlet. So V dot 1 over V small 1 equal to what it was in which unit? It was 7. Yeah, it was 7 meters cubed per minute. So 7 meters cubed per minute. 7, okay, per minute. So I need to divide by 60 over this amount, which is 0.9. Okay, and for volume cubic meters per kilograms of dry air. Okay, so 0.92. And I get my unit from here. Okay, so 7 over 60. Okay, divided by 0.92. So this one is 0.127 kilograms per seconds. Okay, of course, kilograms of dry air. And then 0.127 kilograms of dry air over second multiplied by, okay, here I have kilograms of H2O over kilograms of dry air. Cancel them together and you'll get kilograms of H2O over seconds. Okay, what was the ratio that we found? Okay, it is 16.5, 9.5, 16.5 minus 9.5, this over 1,000, because you want to convert the units. 127 multiplied by 16.5 minus 9.5 over 1,000. So this one is around, okay, 8.89 times 10 to the power minus 4, somehow around this point. Let me just check it real quick. Okay, so this question is question 93. Yeah, question 93. Okay, my amount is, yeah, okay, correct. Okay, he calculated in kilograms per minutes. Okay, so we can maybe manage to do that. Okay, kilograms per minute divided by 60, by the 7 by 60, and then 0.9. Oh, there's something that I didn't correct maybe here. Yeah, what I did, I said 7 over 60 over 0.90. Okay, well, you got the idea. So it is 0.13. Okay, so here we multiply by 0.13. What's going to be the value? It is 9.1. Okay, 9.1 times 10 to the power minus 4 kilograms of H2O per seconds. If we want to find the kilograms of H2O per minutes, then we multiply our answer by 60. And we're going to find that it is 0.0546 kilograms of H2O per minutes, okay, which is the very close to the value in the book or in the solution manual. It is 0.543. Okay, so we had only small errors from doing it here by my mouse, but sometimes you can get very unlucky if you don't pay attention or you just slide it like that. So it is better to practice it using a ruler. Okay, much better than the situation that I'm here now. Okay, yes. So next time, inshallah, we'll do a question about maybe heating and humidification. Okay, heating and humidification. It's very easy. Same thing, just as now we did evaporative cooling, but now we will go in this way. So have simple heating first, then humidification, spraying. And then this is your net process. On the amount of heat, then it is going to be H, okay, minus H here, okay. Not the net heat transfer, but I mean the heat transfer in the cooling coil, okay. And then if you want to know what is the humidity that was added, so omega, and then multiply by that. Okay, you want to know what is else? What else do you want to know? Yeah, you want to know the latent heat, okay, from this humidity. Then you're gonna do this omega minus omega multiplied by H. Okay, omega minus omega multiplied by H. Okay, no, omega minus omega. Yeah, the latent heat. This is the latent heat. Yeah. Sorry, H from here and H from here. We'll look at it next time, inshallah. Okay, and with the mixing process also, we have the mixing process. Okay, so here you have an outlet stream, and also we have the cooling towers. It's also a mixing process, but in disguise. Okay, using like a certain mechanism. Okay, we'll see it. But for now, focus on learning or knowing how to select the points in the psychrometric charts, try to do simple processes. Yeah, simple heating, simple cooling, these stuff, and try to do those two problems that we solved, okay? Those two, one with evaporative cooling and this special one, okay, the only one that we have in the examples with heating and cooling simultaneously, okay? So yeah, see you next time, inshallah, and assalamu alaikum.